we'll start with what we have done previously. Before recap, who is willing to give an explanation or at least say the process what has been done? Anybody? Don't worry if it is wrong also, you will not forget. Very good.
Sir, about the cells, the cell is first, as we all know, the composed of CaCO3, chitin and protein. First we have to demineralize with the help of the HCl, and after that we used to deproteinized with the help of protein. We will get chitin, and after we uses deacetylation with the help of NaOH, we will get chitosan.
So what you exactly did?
Sir, we means procedure, sir.
Yeah.
Sir, first we take HCl. We put HCl in the
HCl was 0.2 molar.
0.2 molar, sir.
Okay.
And after that we left it for 2-3 hours. Then we left it for drying, wash it.
Okay.
And after that we put NaOH 0.5 normality molar, sir. NaOH.
Okay. Nowadays it's only molarity which is used. Normality is no longer in existence. That's fine. Yeah. Good. Yeah.
Yes, sir. After that we left it in the oven for overnight or 6-7 hours. Yes, as sir told us.
That part is not yet done.
Yes, sir. Not yet done.
Yeah.
Sir.
Okay. So basically when we try to see the process, it's better to go in a very, very systematic order. Yeah. It's good. Otherwise it becomes difficult. That's why we call it SOP. Yeah. So first was, the background was shells were collected. Yeah. You can ask all those questions to your instructor who went to different places to get the shells for you. Yeah. And it's a best saying, seeing is believing. When you see it, then you feel that it is how easy it is to do it. Yeah. So shells were dried. So one option is you grind it. Since the hard shells are there, grinding takes too much of energy to grind it, and you need a specialized type of blades to grind it. Sometimes cement, concrete crushers are used to grind those type of shells. Yeah. So these dried shells, as your colleague mentioned, you do first demineralization followed by deproteinization. Yeah. So then deacetylization in another step. Yeah. So what was the thing? You took 1:20 ratio, 0.2 molar hydrochloric acid, and the other acid was acetic acid. Yeah. That was basically 2%. Yeah. 2% acetic acid solution. So it is better to go back to your basic chemistry book, understand molarity and understand percentage of solution. Yeah. That is very, very important and very, very basic. Yeah. So in school, when we all studied science medium, nobody is from arts and humanities, right? All are from science background. Yeah. So what is 2% of acetic acid solution corresponds to how much molarity? Yeah. I use these two solutions interchangeably because if we are telling an industry, you just tell them that take 2 kg of this, mix it in 100 liters of water and use it. Yeah. If you go to a fisherman, said take 2.2 molar, what he will say? He won't understand. Yeah. And there's no point in explaining all those things. Their purpose is to solve the problem. Yeah. So there what scientist lacks. Yeah. You go to a doctor, he gives you medicine. Yeah. You don't ask how it is being encapsulated, whether the paracetamol is encapsulated into starch or how the paracetamol has been crystallized. Yeah. Those are the scientific questions. Yeah. Whether that starch in the tablet is of tapioca or from banana. Yeah. He doesn't explain you all those things. Yeah. Because that's of no point in doing it. But when one pharmacist is talking to another pharmacist, their explanation makes sense. Yeah. So this is what you have to have clarity. Sooner you get into your head, it makes things easier. If you cannot explain a process to 6-year-old child, that means you yourself don't understand. That's the famous saying by one of the great scientists. Yeah? Make sense? So, molarity and percentage of solution. It's very simple. I'm not going to go into this one, but you should be able to understand that. Yeah? Molarity is quite easy. You just get the molecular weight and measure it into ml. Yeah? So, similar thing becomes percentage or so. Yeah? A. Second question is, why only these two acids? What if I use H2SO4? Yeah? What if I use HNO3? What if I use lemon juice which contains citric acid? Yeah? What if I use a sugarcane juice, add acetobacter aceti to make acetic acid? Yeah? If you want to try experiment, buy egg, chicken egg, put into domestic vinegar, leave it for overnight. Next day morning, you'll see there's no shell left. Only thin layer of skin is left, and all egg and albumin will be there. So this is the way shells can be dissolved. Yeah, it is not only for shells what you have done in NIT over here. Yeah. So these are the couple of questions you should be asking yourself. Yeah. Second one is ratio was 1:20. What if you take 1:10? What if you take 1:5? What if you take 1:50? Yeah. So here you have to get the best trade-off between amount of larger the solution you take, better will be the extractability. But you have to draw a line, because then you have to remove that water or you have to discard that water. Yeah. That is another condition. Then comes economic value or economics of a process to decide what is the best part. So every stage is optimized, every unit operation is optimized. And after this, leave it for 2 hours, 3 hours, overnight. Yeah. And what temperature? If you add a temperature, if you add a stirring, how different it will be. Yeah. Think of simple example. You have 100 ml of water, you add 10 grams of sugar, and without a spoon it won't mix. That means stirring will help you in this particular process. If you stir the samples, whatever CO2 is dissolved, it will escape the environment. Yeah. When I say environment, that means environment of that beaker where the sample and biomass was there. So all these things comes when you observe the process. Yeah. Then only you become clear of each and every step. Yeah. Now for that I don't have to read 3 paragraphs of procedure to come up all these points. Yeah. Same thing, if whatever you do, if you make a flow chart, think over it. Why did you do it? Why? What? And how? Yeah. Why you are doing it? Why you are adding, or sorry, why, what are you doing? Yeah. Whatever you did, why did you do it? And then how? So these 3 questions at every stage will make you perfect with the process. Yeah. After this, what was left was the shells were very soft. Yeah. Because cement is gone. Yeah. Something like this, a concrete wall is having a cement, plus you have sand, metal frames and everything. That's the structure of shell. When calcium carbonate, chitin, protein, and if you want to see the structure of a shell, go into any standard book, you will be able to see that layering of that structure. Something like when you are plastering a wall, if you put a small thin metal sheet, plaster it, then put a metal rod in it, plaster it, it becomes very strong wall. Yeah. The same thing it happens. So what you're trying to do is trying to use a solvent to remove one thing which is creating the strength of the structure. So calcium carbonate, protein, this is the structure. So sequentially you are removing calcium, which is easier because a larger quantity, it goes off. Then you are separating the protein, which is again a source of good quality protein, and then you get your chitin. Yeah. You went ahead for deacetylization, which you haven't done it. Yeah. But that is only to convert chitin into chitosan. and chitosan is the one which is also used for making polymeric material. Yeah. Now the challenge is how you can make the whole process in 2 hours, 3 hours, how you can do it in a continuous fashion. All those things are, this is just basic procedure. Yeah. Then you introduce a technology. So if when you, that's the reason when you read a paper, oh, somebody used a microwave for production of chitin. Yeah. Somebody used A, B or C technology. Yeah. Now the question for you is demineralization followed by deproteinization. Can we do other way around? What we did, we first removed the calcium, and then we are removing protein. What if we first remove the protein and then we remove minerals? It is possible. Yeah. So that is both interchangeable. Yeah. So that should be one of the questions, why we are doing demineralization first. We could have done deproteinization first. Why deproteinization only with alkali? Why not with protease enzyme? Yeah. That is also possible. Yeah. So the step for getting to chitin, demineralization, deproteinization, acetylation. But demineralization and deproteinization can be interchanged. Yeah. So if you are doing experiment, you'll do both the process and check the quality, check the yield, and then you come up with the conclusion. Yeah. So this is what you should be seeing in when you look into the publication. Not on downloaded 10 different papers of chitin extraction and then one step forward, 2 step backward, making situation awkward. Yeah. So then you will be only lost in the papers. So to do anything, important aspect is get started. Do some process and then try to improve that particular process. Yeah. How many of you know to make chapatis or dosa? Perfect round dosa which doesn't burn. That's very good. Did you get it in one go? It took multiple time to get a practice, right? Yeah. Same thing. So more and more you do it, same operations, then only you learn better and better operations. Yeah. So this was all to do with practical. So tomorrow what you are going to do is we are going to remove alkali portion. Yeah. And alkali portion will precipitate the protein from shells, and you will also have a fish sample which is dissolved in alkali and a water. Yeah. And then the residual part and the soluble part. The soluble part with the water or with an alkali, when you adjust a pH of 4.5, yeah, this is called isoelectric point of protein. That means protein is least soluble at this pH. But how do we determine this particular point? Why 4.5 pH? For this is also established via experiments. Very similar when you use a nitrogen as a factor of 6.25, 5.7, 6.38. How it is done? If you are extracting a fish protein, the alkali solution what you have, you make pH of 3, 4, 5, 6, 7, 8, 9, whatever, yeah, or even 2 and 1. Alkali solution you have, adjust this pH, and then wherever you see the maximum precipitation, that becomes your isoelectric point, yeah, and that differentiate. But majority of the protein will precipitate at this pH. But very same protein what you get, leftover residue will have acid soluble protein that is called gelatin or collagen from fish. That will solubilize in acid solution that is in and around this pH, that particular residue. So if you add acid without removing the residue, then you are again mixing everything together. Yeah. So what will happen after adding alkali? You will centrifuge it. Alkaline solution you will adjust a pH of 4.5, and once pH is adjusted, you decant the top solution which will still be containing some of the free amino acid, some of the nutrients, acidified water. that water is a wastewater, whereas that can be used easily for production of duckweed, macroalgae or microalgae. That's only you will be able to introduce circularity. Now you might have a question, if you have to use such a small amount of water, but this is only experiment you're doing in smaller quantity. But if you're dealing with 50 grams, you might get in the best way possible from crabs around 5 to 6 grams of chitosan. Yeah? Okay. If this is 50 grams, to get 5 to 6 grams of chitosan, you are already using 2 liters of water. Yeah? Think to make 100 kg of chitosan, how much shells will be required and how much water will be used. Yeah? Now this is the volume what we are talking about. Yeah? So that's the way how things goes up in the order. Yeah? Now by doing so, you are able to get all your chitin or chitosan from shells. Yeah? Any questions so far related to experiment? Now going back to production of duckweed. How do we produce duckweed? Specimen putting in a water and it just multiplies. Yeah? Something like when you want to spread a bacteria, how you spread a coronavirus, exactly the same format. Yeah? Macroalgae. Macroalgae can be grown directly into from spores. But you saw the commercial production, thin rope is tied into one particular metal rod, dipped into the spore solution, taken it out, rope it around a bigger rope, throw it into the sea, forget it. Yeah? That's it. No fertilizer required, nothing else to be added in. Nature will take care of its own and it will produce huge amount of biomass. So per hectare you have a different type of yield you can obtain. And some of the seaweeds can also be cultivated on land with normal pH water. Yeah? That is neutral pH. So when we grow seaweed in ocean or sea, it needs saline environment. What is sea salinity? Loud.
Salt content in ocean.
How much is salt in the sea water? You got Mike by surprise, isn't it? It is 3.3 or 3.4%. Yeah. Have you heard of a sea called Dead Sea? Is there in near about Turkey. Their salt is so high, you can even swim or you can walk on that particular sea. Yeah. In ocean, sea salinity is 3.2 to 3.5% or 3.3%. That much amount of salt is present in it. Yeah. And this is the condition which is required for marine algae to grow. And this much amount of salt water is very high, and for food preservation you need only 0.5 to 1% maximum. Making a pickling, another one. So other one is how best you can use the sea water for making your own pickle. Yeah, getting the sea water, boiling it, and then using it for making pickles. Yeah, then you sell it as no added salt. Technically you are correct, practically you are correct, technically you are wrong. Yeah, because salt was already there. Yeah. So we covered duckweed production, macroalgae, microalgae. Yeah. I have one of the bad habit, when I see something, I'll go and see how it is being produced. If you want to cook a best sweet, go and observe when somebody is cooking it. You did not learn by taking a lecture. You learned how to make your dosa or chapati by seeing how your mother is doing it. Yeah. There was your interest. Either by force you learned it or based on your own interest. Yeah. So when you observe it, ask yourself questions and then you will never forget. Yeah. So that's was what we have covered so far, and now we go on to how do we establish biorefineries. So there will be 3 sequences. One is biorefinery for fish, biorefinery for shells, and biorefinery for aquatic plant. So some of the stuff will be repeating what we have already spoken about. So first and foremost question is, what are biorefineries or new type of biorefinery? We all have studied petroleum biorefinery, yeah? If you see, we do not call it refining, we call it petroleum biorefinery, yeah? So that is not a new word. Even we call it fossil fuel, but they are of biological origin. So once you get mining or you get a crude oil, does anybody know about the petroleum biorefinery? Once you get a crude oil, how we get petrol, diesel, wax, paraffin wax, kerosene, everything in same refinery?
Distillation process, fractional distillation.
Okay, you have a crude oil which is basically a black in color, yeah? And then you heat that oil, right?
Yes, sir.
So whatever vapors goes on top is your petrol, yeah? Then
Diesel,
diesel,
kerosene,
kerosene, then wax, paraffin wax, and all those elements, whatever. So 1 liter of oil will give you different fractions, right? That means same biomass can be fractionated into number of different compounds. Can you suggest any other compound? Yeah? So very same oil, we get number of different compounds. Whereas when it comes to food, if you have wheat grain, yeah? We have done enough for dairy example, now let's move on to wheat. Wheat is milled, yeah? Or wheat is harvested. So what we get? Outer coating, shells. Shell in the means, husk, yeah? And you have a straw. When wheat is harvested, you put it into a thresher, or if you take rice, how many of you have seen wheat processing? That's good, at least one has seen it. So wheat is harvested, it goes into a thresher, or if it goes in a combine, you get husk, you get grains, yeah? And then these grains goes for number of different processes. One is goes for what you call chakki atta, that is whole wheat atta used for making chapatis. Or else this wheat goes through number of different processes where you get wheat germ, yeah? What else? Maida or semolina. What is the difference between maida and semolina? Maida and semolina is the same thing, different particle size. If semolina is grounded into fine flour, it becomes your maida, yeah? And then you have bran, yeah? Same thing applies for rice. This goes for different types of product. Germ mainly contains certain bioactive as well as wheat germ oil, yeah? And similar thing happens with bran as well, and the bran also contains certain type of oil plus fiber called riboxylans, yeah? Have you heard of this word, riboxylan? Have you heard called glucans, beta glucans, yeah? Beta glucan is very well advertised and it comes from oats, that is oats fiber, soluble fiber. Same way wheat also contains riboxylan and same oats also contain. So our main focus is wheat to this atta or this maida atta, yeah? We don't think about what we do with husk, we don't think what we do with straw. Some farmers who are much more advanced, they store this straw for feed purpose, yeah? This is mixed with other green grass to make feed for cattle. Those who have seen the villages, how this type of straw, the straw means the chopped straw, mixed with the water, what do you call that word? Sani? Yeah?
Bhosa. Bhosa.
And when you mix it with the green, what you call berseem and all those things, any of those green grass or other one, and feed it to animal, right?
Normally we call it chara.
Chara, yeah. So that means this is already used as a feed, yeah. What do you call that? It will be different word in different places, yeah. Whereas rice straw is not normally used as an animal feed because it contains large amount of silica, yeah. So you would have seen even when we remove the outer polishing of rice and all those side stream which goes as a waste, to get rice germ oil or rice bran oil, which is also sold in the market. So if you talk everything together, that is basically a biorefinery, yeah. So how a biorefinery looks like this. So from where the wheat will go and from where it will come. This is basically a photograph of a petroleum biorefinery, yeah, or any oil biorefinery or any of those one. If you want to see some of the coal refining unit and all, you can go in and around. You can see the steel refining here in Rourkela steel plant. This is the overall. So we try to establish biorefinery for seafood, for fish, or any of the biomass. Concept remains the same, yeah. Simple one is to fractionate it. So there are number of different definitions for biorefinery. One, a facility that integrate biomass, conversion process and equipment to produce fuel, power and chemicals, yeah. So how you make an assembly together so that you can get energy, power and chemicals. This was one of the definition. Food was out of it. Very few literature you will see on food biorefineries and all, yeah. We are just in a process of completing a book on food biorefineries, and it should be coming out in 1 or 2 or 3 or 4 months, yeah, next few months. So that is exclusively on food biorefineries. It is analogous to today's petroleum refineries, yeah, or sustainable processing of biomass into spectrum of bio-based product. Food is added in, feed is added in, ingredients and chemicals and bioenergy, yeah. The circular part of the seaweed, when we are showing the biomass, conversion, fractionation and storage or whatever you want to use it as. So all these three things together will make a full biorefinery. So why we are moving towards food biorefineries? One, complying with net zero target. That means zero waste approach. To establish zero waste, that means you want to utilize every fraction of it. That means if wheat is produced or fish is harvested from the sea or seaweed is processed, every fraction of that is utilized, yeah. Whether for food purpose or a feed purpose, ingredients and chemicals. So wheat was a perfect example where nothing is wasted, yeah. The straw stored, mixed with the green grass and all to make feed for animal, or you call it simple as chara for animal to eat, and same one it produces milk, so it produces another chain, and cow dung and all if you want to use it for a fertilizer, and the whole wheat grain goes into chakki atta, that whole wheat atta, you make chapatis. So nothing is wasted, yeah. But similar pattern is not adopted for seafood, yeah. Majority of the work, majority of the literature, zero waste approach for dairy is well established. Dairy processing is well established, even though it's a liquid product, yeah. Every fraction of milk is utilized, whereas certain biomass is still having a huge scope to make a zero waste biorefineries. Whether you are working on insects or whether you are working on pulses, even pulses, certain parts are, but not all biorefineries are well established. Second, reducing the greenhouse gas emissions. That means how we can reduce greenhouse gas emissions by valorizing it, reducing the food wastage, and you have already seen what is the impact of waste produced globally and how much greenhouse gas emission it is causing, and can be rated as third country in terms of greenhouse gas emissions according to FAO estimates. Third, to achieve sustainable developmental goals. There are 17 such goals, directly or indirectly how you can achieve those. Transiting economies to an environment, economic and socially sustainable. That means moving E to CE, yeah, or you can call it a general economy to circular economy, yeah, or general economy to bioeconomy. When you establish a bioeconomy, you can again introduce circular. So circular bioeconomy, it becomes B, blue, when you're dealing with marine sources or freshwater species, yeah. Any questions so far with biorefinery? Now, how can we establish a seafood biorefinery? First, what is the requirement of establishing any biorefinery? We need a raw material, yeah. Determine its composition, what all it contains. That is very important, yeah. Without knowing what it contains, how you are going to establish a biorefinery, yeah. And then determine its physico-chemical properties. That means you estimate its properties, how it behaves, how you can store it, how you can stabilize it, yeah. First and foremost, to know what you are dealing with, biomass. Second, define target bioproducts and its physico-chemical properties required. Think of the shells or a fish. If you have a fish, what all it contains? Composition, moisture, 70 to 75% moisture, yeah. 10 to 14% protein, any general fish, 3 to 4% oil, 1 to 2% or 2 to 4% ash, yeah, or within this protein how much is collagen. So you determine all those composition and then try to see what all you want to get out of it. You want to get a whole product, yeah, or you want to establish seafood side stream biorefineries, yeah. Then you make an inventory of technologies or any intervention required to produce targeted bioproduct. This is very simple, plain English to establish a biorefinery. If you want to add any terms or anything is missing, you can interject in between, yeah. First to know the raw material, then what you want to obtain out of it, and what are the physico-chemical properties. That means your target is to get a petrol. Petrol is having a specific density, a specific composition, its flash point, its knocking value, and all those properties are there. And based on that, the processes are established. Same way, if you are establishing a seafood or fish biorefinery, then you need to know what should be the composition of collagen protein or protein of 75%, protein isolate, protein hydrosolate, or protein concentrate, yeah. And then target bioproduct. Make an inventory of input material, yeah. That means what all is required inside. Data collect for each unit operation. That means whatever is operated, you get all the unit operation, and determine chemical compounds to be transformed via pre-treatment or different processes. Whether you have to pre-treat it for stabilization of biomass or for production of different ingredient. Now, once you have done all this, you have to do cost benefit analysis. LCA stands for life cycle assessment. What is LCCA? Life cycle cost analysis. Another one is TEA, techno-economic assessment, yeah. That means whatever process you are making, you make an assessment of it. So experiment what you are doing, some of those experiments are already done, are there in the literature. You make all those questions, establish full biorefinery, then go for execution. Yeah. Before doing all these things, the first question is asked, what will be the cost of this technology? Yeah. That's a wrong question. It's the right question, but at a wrong time. Yeah. What will be the cost of phone? 20 years ago, only elite people were having smartphones, not smartphones, mobile phones. That was this big, yeah. But now everybody is having smartphones. So if that time the inventors of mobile phone were thought it's very expensive, we won't be here, yeah. First you make a process, then improve the process and reduce the cost. That's the way it is always growing process, yeah. So the first inventor of the phone was Graham Bell, yeah. It's not Steve Jobs who made iPhone, but the concept was there, and these are all developmental work or innovations. That was invention, and now all these things are innovations, yeah. That's one is fundamental invention and innovation. That's the difference between invention and innovation, yeah. Any question for biorefinery? If you want to see all these steps for establishing a biorefinery, there are clear-cut guidelines to establish a petroleum refinery or oil refineries in IEA, International Energy Association. Guidelines are there. How do you establish all those refineries? Yeah. So similar type of model can be adopted for establishing any given biorefinery. Instead of C, you can have any other product also, yeah. Or establishing microalgae biorefinery, macroalgae biorefinery, and you will see some of those examples in coming days. So, what is the processing of biomass for valorization? How do we process it? Any sequential order? What will be the next step? First and foremost is stabilization of that biomass. If you have fish waste or a shell waste, how you stabilize it, or what type of pre-treatment you have to do it, yeah. What was done in the case of the shells what you are using? It was cleaned and dried, yeah. So drying is also a pre-treatment, yeah. When I say pre-treatment, that does not mean, oh, something complicated technology. So, conventional technique, drying in hot air, 4 to 6 hours or 8 hours. Using microwave for drying, 20 minutes, drying completed, yeah. Or in some cases, you don't have to do any pre-treatment. So, you can use a fresh shells directly. In that case, you don't have to use huge amount of water. Now, shells which were recovered, they might be having around 40 to 70% moisture. Shells were dried to 5 to 7% or up to 10%. Yeah. Then you are adding 1:20 water. If you use directly fresh shells, which will be difficult to crush, then you don't have to use 1:20. Here what you are doing, you are removing the water, then you are adding the water, correct? To make a coconut chutney, you can use a fresh coconut. I know nobody has tried from the dried coconut, but I have tried with the dried one as well. Still you can make it, but it takes longer and you have to add more water to it, yeah? Using milk directly for making a tea or using a milk powder, yeah? Same situation. So, you can use without a pre-treatment directly a fresh one. Why you are doing stabilization of pre-treatment? Any question? Or why you are doing it? I am asking the question. Why do we do stabilization of pre-treatment? Obviously to stabilize the biomass or to improve subsequent processes. So definition of pre-treatment can be any treatment given prior to process to improve extraction efficiency, preservation of biomass, or to improve extraction yield, number of different rules. Now, giving an example, how many of you know about blanching? Who's going to define it? Okay, give it to you. Yeah.
Dipping the fruits or vegetables in hot water for easy removal of the peel. Potato.
Sudtanni.
Sudutani.
Correct. What temperature?
Hot water. Hot water. Temperature.
Okay. That you said about hot water. Okay. Hot is, so what is hot for you? 40, 50, 60?
Which
I'm asking water, so you can answer it.
I
yeah?
don't know, sir.
Okay. And who was the other one for blanching? Why I'm asking you this? Because this is most commonly studied process in food, right? Yeah.
So blanching is done for removing extra foreign substances also. There are two types of blanching. One is hot water blanching and steam blanching. So according to our needs, the selection of blanching will be done.
Okay. In this case, hot water will be what?
80 to 90 degrees Celsius, I guess.
Okay. And what's the purpose of blanching?
Enzyme inactivation for plants, fruits and vegetables.
That's fine. Enzyme inactivation. Any other?
Sir, it delays ripening and
Blanching. When you put a fruit into hot water, it will not ripen, it will cook. No? No, this side, okay, go on, yeah. And any other step why blanching is done?
So blanching is a pre-treatment operation to inactivate the enzyme in fruits, especially polyphenol oxidase.
That's enzyme inactivation, yeah. Any other thing why we blanch it?
It retains the color retention.
It retains the color, okay. Any other?
It loosens the cellular structures of the fruits and vegetables.
Okay. So these all are very, very technical. How many of you have seen, how many of you made a palak paneer or other one? You've seen spinach is a big volume, yeah? You add into the hot water. So are you inactivating enzyme there? No, right? One is stabilizing the color. What blanching does? Your friend mentioned about your what you call stopping ripening. Sometimes mango fruits and all, they're mixing of 2 or 3 concepts were together, yeah? Blanching is simple as what your friend clearly defined as dipping in hot water or steam. This is done for multiple purposes depending upon the product. If you take a potato, if you slice it, howsoever your mother might be making potato chips, yeah? They dip it in hot water. If you don't dip in hot water, if you fry it, it becomes brown because of polyphenol oxidase, yeah? How this enzyme get activated? Potato is there, it doesn't turn brown. Apple doesn't turn brown. When you slice it, it turns brown, yeah? Because oxygen it gets from the air, enzyme is present, phenolic compounds are there, it acts and makes quinones, yeah? So the moment you dip it in hot water, this enzyme loses its activity. So you don't have to blanch it to inactivate enzyme. 2 ways, cut the oxygen supply, yeah, or make enzyme not to be active. If you slice an apple at 2 degrees Celsius, it will not turn brown, yeah. So you don't have to use energy for that purpose, yeah. So any of the unit operations, that's why you have multiple definition of blanching, because if you would have read the paper, if you read the book or different chapters, everywhere explanation is different, yeah. Nothing is wrong, everything is correct, but you have to see what was the intention of it, yeah. Second one, that was for potato. Other one, hot water dipping is also done to kill certain insects like cauliflowers, yeah. You dip in hot water before cooking. Certain vegetables are dipped in hot water. Cabbage, the moment you dip in the water, it squeezes, volume is reduced. So to remove occluded oxygen, yeah. This explains why color is retained in blanched sample. Oxygen is there, it will oxidize the color, yeah, correct? So for that we remove oxygen trapped in the air, into the plant biomass. The moment you blanch it, air is gone, then it settles down, yeah. So there are multiple one. So this is also one of the important unit operation which is done in a processing environment as well as in stabilization of biomass, yeah. Do you agree? The reason I used blanching word because this is one of the most common unit operation we all study, yeah. Whether we are food or non-food people, we do study blanching, yeah. Blanching before chips, blanching making before spinach curry or any of those food and food ingredient, yeah. Next step goes extraction. By using conventional extraction. How many of you used maceration before? Have seen the maceration? Yeah? Those even we macerate it in ginger and different crops or different biomass. That's one of those conventional extraction or also known as solid liquid extraction. What you did with the shell was simple solid liquid extraction. Other one is by using new technique or hybrid. Hybrid, that means mixing both conventional and new, using ultrasound with the solvent, yeah. That will be ultrasound assisted or microwave assisted, or in some cases you do treatment direct to extraction or direct extraction, yeah. So when you look into the literature, it will, some studies will show ultrasound as a pre-treatment for extraction of ABCD, yeah. Some places will say ultrasound assisted extraction. So remember, there is no clear-cut definition between or no boundaries between these two words, yeah. Okay. Then we get end product. So this is the step for processing of any given biomass. Now come to fish, yeah. So these are some finer details. I have one of our PhD from Inner Mongolia in China. She is working on establishing full biorefineries for seafood side streams, yeah. So these are the waste what we get from fish alone, yeah. NaOH, what you are going to do, yeah, homogenize it, 0.1, 0.2 molar different concentration of acids, yeah, and this is pretty much very standard process, yeah. And then isoelectric solubilization, that means you solubilize the protein, you centrifuge it, this is all what you will be doing, and then you can get lipids, insoluble bones and skins, or else if you are using an enzyme, proteases, you will get your peptides, yeah, or protein hydroslate. If you take a fish side stream, you mince it, what you will get is a fish paste. If you add alkali, protein will solubilize, you precipitate, when you centrifuge it, you get multiple layers, yeah. Then you can separate oil, protein and bones and all, yeah. Very similar, whatever you have done with the shells, same thing can be done over here. And how and where and what should be the step followed, and whatever is left over insoluble fraction, if we do acid extraction, we can get collagen, yeah. It is pretty standard process. You go, even if you put it on normal browser, fish protein extraction, you will see the steps. Put fish oil extraction, get that process. Fish protein extraction, you get that flow chart. Fish collagen extraction, you get that flow chart. Put all those three flow chart together, identify the common step and draw your own process line to obtain multiple ingredients out of it, yeah. That is the best approach. Oh, sorry, this one. Now, if you'll see, fish biorefinery target was to produce protein and peptides. Yeah. Minced fish, this is what experiment you are doing. Adding into a water, or you have added already. Yeah. In water or in alkali. You are not doing this part. After this, when you centrifuge it, you get your supernatant and you get your residue. Yeah. This supernatant, if you precipitate with acid, you get your fish protein. How many of you disagree? As I already mentioned, there may be a lot of mistake in this. You have to pick those mistakes. Yeah. Otherwise, you will be learning wrong things. And I won't be responsible for that, right? So you get a protein. No, nothing is wrong in this. Yeah. So there is no point in scratching your head in this case. So you get your protein, and whatever is left to a residue still is having insoluble proteins. That I said already, collagen or gelatin. Strategies are either to use enzyme to break those protein into peptides or protein hydrosolate, or else use acid for extraction to get collagen. Yeah. And then this is your product B. Whatever A, B, C, D is written, it is clearly written here what does purity and what are the purities it's having. Green color is product A, blue is product B, and C is product C. Product A alone, 1, 2, 3, 4, 5, 6, these are the treatment. If you use only water, because majority of the fish protein is soluble in alkali, yeah. And I'm not going to go with ultrasonics and all unless and until we know about those technology. That will be lecture 16, 17 and in coming days. Control number 4 in alkali, and you can see how much you can get out of it, yeah. So that means protein of fish is alkali soluble. Here what was used was 0.1 molar. What you are using is 0.2 molar. Now the question is, if you use 0.5 2 molar alkali, will you get more protein? This is also very important. One is the pH, yeah. We can achieve pH 12 by using alkali, yeah, or take acidic one. You can achieve pH 3 by using hydrochloric acid, H2SO4, citric acid, acetic acid, lactic acid. Then why we mainly focus on HCl or NaOH? Why not H2SO4? Why not nitric acid? Simple answer is it is easy to handle, yeah. And this is mineral acid, it gives H plus, yeah. H2SO4 will be better option because it gives 2 hydrogens, yeah, 2 hydrogens. So what is the relationship between pH and hydrogen ion concentration? Question to you guys is, if we use higher molarity solution, will you have a better extractability or no? Yeah, because there is no relationship between acidity and a pH, yeah, though it looks like that, because pH is negative of hydrogen ion concentration, varies from 1 to 14, yeah. But if you have a larger molarity of solution, you may not be able to solubilize the protein, because when there is H plus, you need OH also, yeah. And that's why when you adjust the pH, it's not that if you use 5 molar hydrochloric acid, you need only 1 or 2 drops. That's wrong conception. Always you take a weaker acid to precipitate it, yeah. Think of when you have to make cheese, when you have a lemon, you dilute a lemon, then you add into it. Then there is a phase separation proper. Why? If you use directly a powdered citric acid into milk, it will not curdle properly. Yeah? Have you seen it? You make a citric acid or tartaric acid, you make a solution, then you add it slowly while churning it around. Yeah? Have you ever asked why it is done? I'm not talking about the professors or dairy chemistry or dairy processing. Ask the person who make a lot of cheese, chena and all those sweets. They will never add lemon directly. They'll add lemon into the water, mix it, then they add it. Tartaric acid or citric acid, they add into a water and then they add slowly while stirring it. Yeah. So that is learning by experience. Same thing happens here. Yeah. Because the same protein, not same protein, basically protein made up of same amino acids. Yeah. So as you can see, this is having this product A as these two values. And then the residue, if we use enzyme, yeah, there is a specific procedure for that, and you are getting this much amount of protein recovered, both product A plus B, that is, this is also protein and this is protein hydrolyzed protein or protein hydroslate, and you can see how the recovery is changing. Yeah. When it comes to the purity, that means how pure is the protein. Green one is product A here, with water you see 30, 68, 66, 75, 73. Yeah. So you optimize a specific condition to come to a level, what should be the alkali concentration, how much time you have to use it, what technique to use it to get the protein. The next task comes, what you are going to recover next. Yeah. Then when you are left over with bones and scales. Yeah. The similar operations with different techniques. HPP is a high pressure. Yeah. So not to worry about the technology, we'll cover that one. Yeah. Here the ratio was only 1:4, not 1:10, because fish used here was fresh fish, minced with lower water, and then we use two different techniques, one after the other, and now your recovery of these ones is improved. Yeah. So you use a technology based on what is your intention. 82% pure and recovery is increased in every case. Only with water alone you have higher recovery. Yeah. Yeah. So that means high pressure was able to solubilize more of protein into water. Yeah. So these are some of the experimental data, not to worry about all these numbers and a treatment, that all you can play around with yourself. Yeah. So this is very simple process. Bottom line is you have a biomass. Here you can call it high pressure as a pre-treatment. Why high pressure was done? It's not because technology is there, that's why it was used. High pressure was done mainly to inactivate microorganisms. Yeah. When you have a fish biomass, this fish came from the factory, side stream, it was left out, so there will be some microbial contamination, and that microbial contamination will come into this protein because we are not heating anywhere. Yeah. So we gave a high pressure treatment to inactivate microorganisms rather than heating it. But by giving high pressure treatment, we got a microbial inactivation but increase in recovery yield. Yeah. So that becomes the interesting part of the data. Yeah. So here precipitation was done 5.5. This was again, you will investigate what is the isoelectric point. Every fish, source of the fish will have different precipitation point, and this was also changed because of this pre-treatment, because high pressure can also alter the properties of protein. Yeah. So that is one simple example for protein purity and followed by enzymatic hydrolysis. Yeah. Now other one is for oil. Oh, sorry. Other one for oil. Fish drying. I don't do all this animation. This is what keeps happening. Yeah. So for this, again, either you have, I'll leave it on to this one. either you have a supercritical condition or direct oil extraction. Yeah. So that means supercritical, that means you are using liquid CO2 to obtain proteins and followed by alkali treatment to get your protein and lipids together. Yeah. So do you have any way how you can extract your, I'll just leave it on here, extract your oil, protein and peptides? How we can extract oil, protein and peptides together from a biomass? So in the case of fish, it is possible to do drying of fish, yeah, get your oil out using supercritical, yeah, and all the carotenoids and pigment left over biomass, then to go for protein. Or else, if you have a fish which contains 14% moisture, 14% protein, 70% moisture and 5% lipid, the moment you dry this fish, 5% lipids might become 20 to 25 because you are eliminating the moisture. 14% protein may become 45 to 50%, correct? Then if this goes for supercritical fluid extraction or hexane for recovery of fat or lipid, then again this protein may become from 50 to 70%. This is complete dry fractionation route, yeah. And bones and scales can be removed by using simple sieving technique. So when it comes to extraction, either it's a wet fractionation or dry fractionation, yeah. Now, any questions? Supercritical or direct to remove oil, that's lipid, and then followed by alkali treatment or pressure treatment, or to use water to get your proteins, yeah. Any questions? This was a good bit of entertainment, swinging in and out, yeah. Any questions or any question related to protein, lipids or peptides, or how do we establish biorefinery? No? Or any suggestion? So this is really important to see how we can process the biomass, and there are number of techniques, number of conventional ways we can obtain our biomass. So one, establishing a biorefinery, you need to know about the biomass. How do you stabilize so that you can store it for longer? Develop the extraction processes, optimize each and every condition, and then check the quality of the product. If it is not as per your specification, then you alter your extraction technique or condition, or you alter your pre-treatment strategy, yeah. So quick recap is about how do we establish biorefinery. One, you need to know about your raw material, its composition, A, most important element, and understand its properties. Second, what are the target bioproduct? What all we can get from fish is your protein, lipids, yeah, gelatin or collagen, minerals, yeah. And once you have a lipid, then you can get easily your glycerol and fatty acid for further fractionation, yeah. So this is all how you can establish a complete biorefinery by establishing different unit operations, yeah. No questions? No. So tomorrow what you are going to do is, you already have alkali solubilized with fish protein and you have shells protein. You will precipitate that with 4.5 or 5 pH. You will see something is precipitated at the bottom. Once you centrifuge it, bottom one will be protein. If you measure it, it will be around 60 to 70% protein in it and the liquid portion. Once protein is done, this is in the case of fish, whereas in the case of shells, when protein is separated, leftover biomass is all chitin, and that can be converted into chitosan by using high amount of alkali, 50% at higher temperature. So it depends upon your instructor if they want to convert that chitin into chitosan, and you can check its property with commercially available chitosan. At least you can tell, at least this much you can tell, was that experiment difficult or easy? Yeah? Whole of research itself is easy. But we need to be sure of what we want to do and what we want to extract. If you don't know what you are doing, it becomes difficult. Remember, this world is full of two types of researcher. One, they manage what they understand. Second, they manage what they don't understand. Second category is the people who want to manage to show that they are doing complicated stuff. Yeah, that is where the most of the problem lies. Yeah.